Welcome, everybody. I'm Greg Wolverson, standing in as the chair of the Royal Met Society Scottish Centre. Very welcome to you this evening for our December talk. Usually our festive session, so hopefully you've got something nice and warm and a mince pie to enjoy that we sometimes do in person. The talk is being recorded, as we just saw there, and should be available on YouTube in the next few days, pending permission releases. We encourage any questions to be inserted into the whiteboard that you can see there, and I will help facilitate the Q&A as we move through that. So I want to just introduce our speaker and begin the session. So our speaker tonight, we welcome Professor Zhongbo Shi from the University of Birmingham. Professor Shi started his career as a geologist before undertaking his PhD, where he investigated physiochemical properties and the bioreactivity of urban aerosols and dust in Beijing. His following research in both China and Japan included research on fog and haze processing of primary particles and the sources of urban aerosols, also the aging of the Asian dust and its impact on the chemical compositions and hygroscopic properties, and the atmospheric processing of iron and phosphorus in mineral dust. He joined the University of Birmingham in 2011 as a NERC Fellow and also the first Birmingham Fellow, and was promoted to Professor in 2020. His current research aims at improving the estimation of the deposition fluxes of bioavailable iron, phosphorus, and trace materials to the global ecosystems. This is approached by a combination of field measurements, laboratory simulations, and global transport modeling simulations. So the talk that we are going to get tonight, the title is Beyond Clean Air Zones and Traffic Electrification, Lessons from COVID Lockdowns and Clean Air Interventions. So the summary is that air pollution is the single biggest environmental risk, causing approximately 30,000 deaths and £20 billion of economic loss every year in the UK. Improving air pollution will not only benefit the public health, but also the economy. In the past few years, a range of air quality interventions, whether intentional or unintentional, were implemented, which offered great opportunities to examine which measures may or may not work in improving air quality. So in this talk, Professor Shi will firstly introduce a novel machine learning and synthetic control approach to evaluate these interventions, and will then quantify the impacts of COVID lockdowns, clean air zones, and low emission zones on air quality. And will finally outline whether clean air zones are effective in improving public health, and also explore whether traffic electrification is sufficient to improve the UK's air quality to meet WHO guidelines for protecting public health. So I will hand over to our speaker. You're very welcome, and we look forward to the talk.
Thank you very much, Gregory. So I'll just try to share my screen. I wonder whether it can you see my screen?
It's blank just now. There we go. Let's come up.
Right. So, my title is Beyond Clean Air Zones and Traffic Electrification. Lessons that we learned from the COVID lockdowns and clean air zone interventions. So first of all, I'd like to acknowledge LERC for funding and the University of Birmingham Institute of Global Innovation Clean Air theme, which I co-lead, and also a number of colleagues for their contribution to what I'm presenting here today. So why should we care about air pollution? So Gregory has just mentioned that in the UK, every year we have roughly 30,000 people die prematurely because of air pollution, and the economic cost is roughly about £20 billion. If you look at that on a global scale, air pollution, let me try to find the laser. So air pollution is the second most important risk factor, just below the high blood pressure. So It's also estimated to cause roughly about 7 million premature deaths globally. And in the State of Global Air report, the air pollution is estimated to cost roughly about 7 million premature deaths every year. Also, we should remember that they could also make people sick. And as a result of this, you have lost days. On an average, you're talking about 93 billion days lived with yearless in 2019. So you lost productivity as well. And I also mentioned a little bit about the air pollution cost on economy. So this World Bank report estimated that the cost of health damage from the PM2.5 only. Remember that air pollution is not just about the PM2.5, which I'll introduce a little bit later. There are many other air pollutants, such as nitrogen dioxide or ozone. So if you only consider PM2.5, you're already talking about a huge, impact. This is South Asia, including India, for example. But obviously in North America, it's smaller, but even that is a huge impact on a GDP. So I mentioned a little bit about PM2.5. So PM2.5 refers to the particular matter that is less than 2.5 micrometer. So to think about it, the diameter of our hair is roughly about 70 micrometer. So it's about 35 times bigger, about 30 times bigger. So it's really, really, really small. So PM2.5 is the particles that are able to enter into the lungs, particularly the upper parts of the lungs. PM1 is the particles that's less than 1 micrometer, and it can get into the depths of lungs. But if you look at the particles, which we call PM0.1, we call them nanoparticles. They can enter into our blood streams and being transported to anywhere in our body, including our brain. Just have a think about it. Even when you're in Scotland, which is much cleaner in terms of PM2.5 pollution, we're still talking about every breath you take, you are taking 2.5 million particles, massive number. So over every single day, we are talking about 5 to 15 billion individual particles being inhaled into our body, and a proportion of this is going to get into our body, and we have to deal with it. And that is one of the reasons why this, particles are so damaging. Now, this figure shows the actual measured not PM2.5, nitrogen dioxide concentration in Edinburgh. It's Edinburgh Nicholson Street. Now, what you can see from here, so X is the date from the 1st to 31st of October, and the Y-axis is the concentration. What you can see here is you see a massive variation, hour by hour variation. Sometimes it goes close to zeros, other times goes, nearly 80 microgram per cubic meter. So what controls this massive variability? The first is metrology. So in the short term, which I'll explain a bit later, in the short term, metrology dominates the variability of air pollutant concentration under the same emission conditions. Obviously, there are also other factors. For example, during the rush hours, there are higher emissions, which also contribute to the variability, and there are chemical processes taking place as well. So there are 3 processes: emissions, metrology, and chemistry. All of this contributes to the variability of air quality we are experiencing. Now I'm going to go to give our first example about the COVID lockdown and its impact on air quality in the UK. So we all remember that on the 23rd of March 2020, the UK has its first lockdown. And many other cities across the world also has lockdown, and the media has been crazy about this lockdown effect. So one of the things they show, for example, this is the Indian Gate, where they show two photos, try to demonstrate that the lockdown has a huge impact on air quality. But remember, we just talked about meteorology and emissions and chemistry, all three processes. By taking a photo from different days, you can't really tell whether that is because of lockdown or not. So in our study, we have to try to get rid of the meteorology effect to really understand the emission changes because of the lockdown. And this is the BBC News as well. So how do we normally quantify the effect of our particular intervention? In this case, it's the lockdown. So the most used methodology is air quality modeling. So by doing scenario analysis using air quality models, you can then try to understand the impact of meteorology and emissions. So this is a study where they have demonstrated the impact of meteorology that is, causing an increase, emission causes an increase, and in total, that's how you would see. But what we are trying to do is using observational data. So in this case, the BBC used the data from DEFRA Air, where they compared the concentration of nitrogen dioxide in 2019 with that in 2020. And they say that this difference between this 2019 and 2020 can be assumed to be because of the lockdown effect. This is where they show us here. This is the same period, 2019, and the period in 2020. You can see a massive difference. The potential issue I'll explain a bit later. So one of them is, again, meteorology are not necessarily the same during this period, and meteorology plays a huge role in the air quality variability. So in our study, we have applied our machine learning approach. We collected data from 11 cities. We're using a machine learning to get rid of the weather effect. I'll explain a bit later. I don't want to give too much details about the machine learning approach itself. But first, I would like to show our machine learning model performance. So what we normally do is we're using a proportion of our data, about 80%, we build our machine learning model, and then we use 20% of the randomly selected data to validate our model. So this is the validation result. We in comparison with our results, this is the yellow dot suggests a very good correlation. But the air quality modeling, people are using for their study quite often wouldn't be not very good. Although if you look at this correlation with the blue dot, you still got a really good correlation. But if you do that, if you get rid of one single data set, you're going to get a really, really poor correlation. So usually, if you're using a regression model, your R square usually would be, range from 0.3 to 0.7, but using the machine learning model, the performance is usually much better. 0.9 is very normal. So when we build our model, then we can, we're confident with our model. So we know the model is working, is predicting the real measured air quality well, then we can estimate the average concentration or the concentration of the air pollutant during an average meteorological condition. So the average could be over a particular period of time or the average over a 30-year period. So whatever you do, you just average you put your meteorological data as dependent variables, put them in a model, you get the average meteorological conditions in a model, and now it predicts the concentration. So this is what we did. So if you look at the nitrogen dioxide concentration, this is in Wuhan, where this is the lockdown date. Oh no, it's not Wuhan. This is, I can't remember where is this now. This is the lockdown date. So just before lockdown, your NO2 concentration very high. Just after that lockdown is very low. We're talking about nearly 90% of drop in nitrogen dioxide. But you cannot attribute this to the lockdown itself, because we know that meteorological effect is impacting them. Now, if you look at that, this and this, we are seeing massive changes, but that have nothing to do with the lockdown. When we get rid of the weather effects, where we call weather normalization processes, to get the de-weathered concentration, this is what we get. So under the normal, the average meteorological condition, this is the concentration, but because of the meteorology during this period is really bad, so the concentration is higher. On other times where the de-weathered concentration or the concentration during the average meteorological condition is higher than the measured ones, because the meteorological conditions are very good. Now, you can also see this, weekly cycle, in a weekend where the concentration is lower. So you understand that we know during a weekend the concentration of air pollutant and NO2 is lower because there are less cars on the street. But doing that, we can see the actual change is much, much smaller than that. Now I'm going to show some of this data here now. If you look at the data from a few of those cities, we can see that, for example, in Beijing here, you see a sudden change during when a lockdown began, and sudden change, this nitrogen dioxide, and it can see a sudden increase in ozone pollution. And a sudden change here as well in Wuhan, not so much in London, interestingly. You can see that sudden change in Paris. So this is the 2020. If you look at in the 2018, you don't, during that lockdown date, you don't see that. You don't see that. You can see a gradual change, a gradual increase in ozone concentrations, but you don't see sudden changes. You do see some sudden change at some point, but that is not related to particular event, which we don't have the data. But you can see this all really clearly here, a sudden change. I'm not going to go too much details about the chemistry taking place. What we see here is NOx, so nitrogen dioxide is dropping, and it's dropping abruptly, but the nitrogen oxide as a whole, which is the nitrogen oxide plus nitrogen dioxide together, the change is much bigger. This is so NOx is where the emission comes from the traffic. So the traffic emissions or NOx are actually bigger than we see from NO2 due to ozone titration effect. Let's not go too much details about that. The other thing we have to consider that is during a period of time, for example, in the last 20, 30 years, in the UK, nitrogen dioxide concentration or nitrogen oxide emissions are reducing all the time. So whether you're going to have a lockdown or not, that trend is going to continue because of the changes in the vehicle fleet. For example, newer cars get on a road where the emissions are lower, and the older cars, the more polluting cars, which contributes a lot to the pollution, are being phased out. Now, remember that figure that BBC I showed earlier, where they compared that between 2020 with 2019. They say, okay, well, that is the difference here. That's the difference. Suggests a change, a fallen in NO2 because of the lockdown. But remember here, we say whether you're going to have these lockdown or not, that concentration is going to change anyway. And it does demonstrate here, where you can see here, although, you know, overall there is a 1 week where the concentration are almost the same as the week in 2020, but overall, if you took an average, it's much, much slower. So if you calculate the lockdown effect for this as what you believe it is, the actual lockdown effect is much, much more overestimated. This is why we have come to an idea of detrending. So in 2018 and in previous years like 2019 or 2017, in general, from the winter to the summer, you are seeing a decrease in nitrogen dioxide and an increase in ozone. And this trend is consistent over the years. And that is because of the nitrogen dioxide, for example, emissions has been reduced when it goes out of the winter, where there are fewer heating needed, so the emissions will be reduced. And in the ozone is because of the chemistry. When when you get into the spring and the summer, where there's more photochemistry taking place, so that trend is always there. Now, if we compare the concentration during this period, which is during lockdown, with this period, which is before the lockdown, what you can see are big change. The change is massive. But a part of this is related to this lateral change. It's a change whether or not you have a lockdown. So if we know the rate of change from the previous years, then we can predict, based on this data, what the business as usual conditions will be, and the difference will be what we calculate as the real difference. Now, this figure demonstrates the real changes and the observed changes. Taking nitrogen dioxide as an example, so the observed changes during lockdown and before the lockdown is 40%. The actual changes, it's about 18%. Ozone, you look at the ozone, so you can see the NO2 in every cities, all of them, we see a decrease, sometimes more, sometimes less. But what you can see clearly is in all cases, the real changes are much smaller than those observed changes. As I said earlier, that is because of you always have a lateral trend of decreasing NO2 from the winter to the summer. The other thing to note is that the ozone concentration always increased during the lockdown in comparison to before lockdown. And part of this is because of the lateral increase in ozone concentration. And that's why the real changes are much, much smaller. Now let's have a look at the PM 2.5. Again, those dark colors are the de-weathered data, and the lighter colors are the real measured. So you can see a very, very spiky in all of those cases. What we can see from those de-weathered data is that you look at Los Angeles, so we can see our sudden change just before the lockdown began, but lower, in other places. In Paris, we actually see a sudden increase, and in London, we didn't see much change at all. In other places like Wuhan, we didn't really see a massive sudden change. In Beijing, we actually seems to see an increase in the PM2.5. But in Beijing and Wuhan, after the few days, you can start to see the effect. Now, the increase in the PM2.5 in London and Paris, so there actually, from the data, it's not very clear, but you can actually see a little bit of an increase here. And during that period, the increase is associated with the increase in the PM2.5 to PM10 ratio, and PM2.5 is largely secondary in nature. It's basically they are formed in the atmosphere rather than direct emissions. And the PM2.5 to our primary tracer of carbon monoxide also are higher during those periods, suggesting that the secondary formation has been increasing during those periods. So I'll talk a little bit about this later in other cities and explain why this could be the case. But overall, we are seeing an increase in PM2.5 in some cities, although we have a lockdown, but there are decrease in other cities. It's not a consistent picture for PM2.5. Okay, now let's have a look at the clean air zone effect. So the Birmingham clean air zone is around the ring road. It starts on the 1st of June. It charges for the polluting vehicles, but no charge for other vehicles. So first of all, we do our de-weathering. So we applied our machine learning model to de-weather the data. We can see a stronger, weekly variation here, which makes sense. And it does seems to see a change from this week. And after this is lockdown, this is the implementation of clean air zone. So you can see that before and after, it does seem to see a decrease. And then we applied our economic model method called synthetic control. So the method is based on our Nobel Prize winner developed method. Here is an example of California. So on a y-axis, you can see per capita cigarette sales impacts, and this is the 1999, the passage of the proposition. This is an intervention, we call it. So the California, the per capita cigarette sales has been decreasing all the time. And the rest of the United States is decreasing, but the trends are not necessarily the same. So how do we estimate the real impact? Because it has been decreasing already during this period. So if you want to evaluate the real impact of this policy, you have to try to find out our business as usual predictions. And this is what we call a synthetic control. So the model is going to be based on the data from the other 49 states. And the model is iteratively calculate the putting our weight on each of the state, on a data from each of the state randomly, and they did thousands and tens of thousands or millions of times of a recalculation, and they come to one synthetic control where it is able to simulate this particular period, so before the policy implement. And now you extrapolate that to the whole study period, and that you get the synthetic control. So if you're able to get this period correct, the rest you should have confidence with it. And this is what you would have looked like without this policy. And now you can see the real policy effect. So we applied the same methodology here in our data. And here is an example where this is the synthetic de-weathered nitrogen dioxide. I have to mention that we have to get rid of weather. If we don't, we're in big trouble because all of the data doesn't make sense. The weather effect is massive. And if we were able to produce this pre-implementation very well, so we have confidence of the synthetic control. And the real de-weathered concentration is like this, and the effect of the clean air zone is going to be like this. We can normalize this where we get this, the pre-implementation period to be close to 0 and the real effect to be shown here. This is essentially the same as we mentioned. So we did see our significant effect later on, but not immediately, but later on in the inside the clean air zone in Birmingham. And this is the roadside data. I'm not going to go to too much details about this. We have 8 sites and we look at each of the sites. But one of the things I want to highlight that is, for example, in this roadside site, we are seeing roughly up to about 5 microgram per cubic meter of decrease in nitrogen oxide. But the decrease in nitrogen dioxide, the nitrogen oxide decrease is much bigger. It's nearly up to 20 microgram per cubic meter. Again, this agrees with what we understand because of the when the nitrogen oxide is reduced, part of this nitrogen oxide will be oxidized by ozone to make nitrogen dioxide. So the actual nitrogen dioxide concentration is higher. Now, if we look at all this data, this is within a clean air zone, this is outside a clean air zone. So we can see this, if you look at the observed changes, after, during the implementation of the clean air zone, comparing to the to before, you can see a big change in all of those sites. But if you look at the real changes, this is the red one is the real changes. You can see at the roadside, you have, about 12%, different roadside, and this is another roadside, it's about 15, 20%. But in the urban background side, where the change is really small. So really, when you implement the policy, the roadside concentration reduced, the urban background concentration does not change much. There are very few people living right next to the road. A majority of people living within the urban background areas, and the change is really small and not significant, statistically significant. Within the rain road, we see the decrease as well, but outside those clean air zones, if you look at the observed data, sometimes you see that is massive changes, but the real difference, the real change is really, really small. It's not statistically significant. And that is a really important point to remember, that if you just look at the observed data, you get the wrong result. And that is not only the city councils, the Birmingham City Council is probably using the observed data. And I also believe that Department of Transport, when they evaluate effect of London low emission zone, they also use the observed data, and I don't feel that is appropriate. But if you look at the impact on the PM 2.5, so this is again the urban background where most people are living, we are seeing almost a low change in PM 2.5. And this is within the clean air zone, the two sides, and outside clean air zone. Not surprisingly, we see no change. We detect no change in PM 2.5. So basically, the clean air zone from the Birmingham has very little impact on the urban background nitrogen dioxide. It made the compliance. The main purpose is to try to make sure the roadside concentration of nitrogen dioxide is compliant. They succeeded in doing that, but their impact on nitrogen dioxide and the PM 2.5 are minimal. We have using our air quality and health model to estimate the health benefit from the clean air zone for the first year, and our estimate is that is saved 1 premature death in the West Midlands, where there are roughly about 900 premature deaths every year in the region. So that you're only saving 1 premature death. So that to me is the clean air zone is an effort to try to be compliant with the legal limit, but its health benefit is very small, particularly when you're considering the huge economic cost to that. Now, we have talked about PM 2.5 from the lockdown. It's really hard to control. You don't really know, when you will see an increase, and sometimes you see decrease when you've got an intervention. And we also say that you have a clean air zone, it doesn't really work on PM 2.5. So why that is the case? So this is another paper that's published in National Science Review, where they compare the PM 2.5 changes after the lockdown in China. A lot of this is a decrease, but you can see in the northern part of China where the concentration actually increased. That I have showed a bit earlier already. Now, one of the reasons is that PM 2.5 composed 2 parts. One is we call it primary emission. That is basically the particles that's directly emitted, let's say from road traffic, where sometimes you see the black smoke. So that's black smoke particles. But a majority of the PM 2.5 in the UK is secondary. When I mean secondary, I mean those are the particles that are formed in the air from the gases. For example, you got nitrogen dioxide from traffic, and they are converted in air to nitrate. And a lot of those secondary sources are from regional source rather than formed in the urban atmosphere. So looking at the London, Paris, and Berlin, you can always see an interesting trend here, where the rural background side is lower, urban background side is a bit higher, and road side is much higher. So from the rural background to urban background, the difference is very small. We're really talking about 80% of the particles are generated outside of the urban areas. In this case, for example, London. So even if you get rid of all the pollution from London, you're not going to get, if you don't do anything else, don't control pollution from elsewhere, your PM 2.5 concentration decrease is going to be really, really small. Same thing in other places. What is really annoying is there is a non-linear effect of PM 2.5 response to the precursor emissions, for example, sulfur dioxide or nitrogen oxide, which are eventually converted into the particles. So in this case is when the nitrogen dioxide reduced by 80%. But if you look at the nitrate concentration here, it's actually initially it's increasing, and then it starts to decrease. So it's not linear. And this is really complex because of there's a very complex chemistry taking place in air. And this is another example showing the sulfur dioxide concentration in Beijing, where it's decreased from, this is decreased by more than 80%. But if you look at those sulfate concentration here, it's only decreased by 60%. And that is because of the conversion rate of sulfur dioxide to sulfate has been increasing during this process. So even you are reducing the precursor emissions, it does not give you the immediate benefit. And it sometimes could even cause the pollution to increase. But of course, if you really keep reducing this to a certain point, then you will see a bigger drop in the concentration of the PM 2.5. But will traffic electrification solve our air pollution problem? I will show a figure a bit later about nitrogen dioxide, but first of all, let's show the non-exhaust particle emissions. Now, this is the emission factor. Is basically, every vehicle travel for 1 kilometer, how many milligram of, let's say, tire wear particles are emitted. This is the brake wear, and this is the resuspension, and this is the road wear. So what we can see here is that from the x-axis, so when the weight of the vehicle is increasing, the emission rate are increasing. Obviously, it to some extent dependent on the type of road, but in general, the trend is clear. The higher the weight of the vehicles, the higher the emission. Now, we do know that the because of the battery, the electric vehicles are heavier. So we're not going to help reducing the non-exhaust particles by replacing the diesel or petrol cars with electric vehicles. Now, the other thing that our colleagues have done is that they make an assumption that, okay, let's see, 100% of the bus are electrified and 50% of the passenger cars are electrified in the West Midlands. This is the West Midlands. Now, what you can see here is if you look at the nitrogen dioxide, over those major roads, you'll see up to nearly 40% of decrease in the nitrogen dioxide. So it's really make a really important impact, even in those urban background areas. You are still seeing significant changes, which is good. But will that resolve our problem of PM 2.5? Well, basically the answer is no. The impact is really, really small. You can see in this major road, you decrease up to 10%. A majority of those is, about 2% of PM 2.5, and that is, you have very little benefit. But fortunately, our net zero strategy has a potential co-benefit on air quality. So this is a Royal Society report where they look at the different sectors and how that might affect air quality in general. For example, electric supply, net zero policies would improve air quality. Transport usually improves air quality. Agriculture again, usually improves air quality. But there are always, other possibilities where it could potentially affect air quality negatively. Behavior change is highly uncertain. One of the things that, if we continue to push for electric vehicles rather than just get rid of those road traffic, is that people will feel that, okay, my vehicles are clean, so I'm going to use it more and more. And that not only going to cause congestion, but also going to cause increase in the non-exhaust particles. That's not going to be, helpful for improving air quality and reducing their health impact. Again, this is a study by our colleagues within our department where they showed the net zero scenario and the business as a usual scenario. You can see if you are implementing net zero policies, we're seeing a decrease, significant decrease in the nitrogen dioxide concentrations. But if you, again, even if you look at the PM 2.5, we're looking at more than sometimes up to like nearly 20% decrease in the PM 2.5 concentration. So it's really beneficial overall. We also note that there are huge inequality in air quality exposures. Here we show the PM 2.5 in the different ward in the West Midlands, where you can see in some of the ward the concentration of PM 2.5 are much higher by up to 20%. But because there are a lot more people living in those highly polluted areas, so the population weighted exposure are hugely different. I was really surprised by this when I saw this. But what you can see here is in those dark areas, you're talking about several times, 4 or 5 times higher. So the population weighted exposure are much higher. So if you really need to make a progress in improving public health, this is the areas where more efforts needs to be put into. And also not just load that nitrogen dioxide. PM 2.5 is the most important pollutant, and the effort needs to go to PM 2.5, and the effort needs to be put into the into those most deprived regions where the population exposure is much higher. So we do need to take a systems approach. We need to make sure that any policies we're implementing will not have a negative or have a minimum negative impact, as we talked about a bit earlier about the electrification of road traffic. It is good to some extent, but it can potentially lead to negative unintended consequences, such as increased traffic overall and increased non-exhaust particle emissions. But also we really need to take a health-centered approach. We can't just simply say, let's try to make efforts in compliance to reduce nitrogen dioxide, but more importantly, it is to reduce the PM 2.5, which is the single most important air pollutant. So to give a summary, meteorology is determining the short-term air quality changes, and that is a really key concept that not everyone is taking, even in our in our field. I'm really surprised about that. And a lot of those in the policy making arena don't seem to take this into account when they are evaluating the impact of the interventions. They don't take into account this meteorological impact. And we do know in the future, when the climate is changing, there is a potential to cause poorer air quality, including the increased ozone and increased PM 2.5 concentrations. what we have seen from the COVID lockdown and the clean air zone is that nitrogen dioxide have dropped abruptly, but the real effect is not as big as we observed. And we know that partially could be because of the other emission sources, such as residential heating, are contributing to the nitrogen dioxide, and the industry as well. And we also know that ozone have increased abruptly after the COVID lockdown began, and that is because of the chemistry taking place, and that is partially a problem we need to avoid in the future when we are devising our policies to minimize the impact on ozone. We do know that PM 2.5, sorry, it's not decreasing in all cities, decrease in most of the cities, but not in London and Paris. And we haven't seen abrupt changes, probably not surprising, considering a lot of those are secondary in nature, so it takes time for that to take effect. And we have seen very little benefit of Birmingham Clean Air Zone, particularly in terms of health. And it does have major impact on nitrogen oxides. It does make the air quality compliant with legal limit, health benefit, very little. So we need our systems and health-centered approach. We need to focus on PM 2.5. We need to focus on the areas that has the greatest inequality to maximize our health benefit of air pollution control. Thank you very much for your attention. If that's any questions, I'm happy to take.
Thank you very much, Professor Shi. That was fascinating, and I've been taking notes throughout and trying to keep up with it all, and really nice to see that kind of real world example and relevance. So yeah, that was fantastic. Thank you. We have got a few questions in. I've got a couple myself as well, actually. The first one, I'll start with kind of a basic one, actually. I'm a meteorologist, and we're a meteorological society. There's a lot of talk about removing the meteorological effects and the de-weathering process. I appreciate it's not a massive part of your research, but can you give some examples of what the meteorological effects you're talking about that you're trying to remove, if that makes sense?
Just to give a simple example, for example, if when there is a really strong wind, very windy, so air quality usually are much better because the pollution in the urban areas has been blown away. But those, we don't always have high wind. We have low wind days, high wind days. So over a period of time, let's say over 10 or 30 years of time, we know roughly during that, maybe in January, we have a kind of average meteorological condition. So when we predict and we build our models, then we put that average meteorological condition in the model can spit out the average air quality. Hope that makes sense.
It does, thank you. Yeah. Let me just. Okay, we've got a question from Vicky Ingram, and she asks, do we know what the impact of climate change will be on air quality as the weather changes? If traffic levels stay as they are now, would we see some areas improving and others worsening if we take climate change models in?
It's a really good question. There are growing number of research in this area now. In the UK as a whole, we don't really know yet whether some areas will be benefited, others will have disbenefit. What we do know is in some places, some studies in China, for example, which have showed that the PM 2.5 concentration will be increasing, the haze, conditions, because of the climate change. You will have more for the UK, for example, you will have more higher temperature, extreme weather days, heat waves, for example. And we know during the heat waves there will be higher pollution, particularly ozone and PM 2.5. And that is one of the things that we're predicting is going to happen. So it's not going to help. And I think it overall is going to be that the impact is probably quite regional rather than a specific, let's say, on city scale. So the impact is likely to be on a much bigger scale, probably the whole of UK in general. It's likely that it's going to be having a disbenefit rather than a benefit.
Understood. Thank you. That's very clear. Some other questions that we have. One question is, do you have data just outside the clear air zone boundary where the displacement of non-compliant traffic may lead to greater concentrations? So as the traffic gets pushed elsewhere,
yeah, again,
I guess is there a limit to how much you can observe?
Yeah, this is a really good question as well. What we have actually looked at those data, including on a rain road. So when rain road is not controlled, we didn't see a displacement effect actually. And if we look, we do have sites outside the clean air zone, and we didn't really see a displacement impact. We're still trying to understand what is going on. And if we have like traffic data, we'll be able to better interpret this result. One of the possibilities is that some of those vehicles that are not compliant, they might just not get into Birmingham, rather than not just the clean air zone itself. You might not just come to Birmingham, but we don't have definite answer to those.
Understood. A few more questions, if that's okay, if you've got time.
Yeah, no problem.
Another one is whether you have looked, I mean, you talked and you made it quite clear that PM 2.5 is the most important pollutant. Have you considered PM1 and PM 0.1 concentrations? The question suggests that some research might indicate that modern tyre wear will increase microplastics with ultrafine particles, so larger mass emissions, but these emissions made up of even smaller particles than currently emitted. So is there research to be done on the smaller particle emissions?
Well, yes, we're working on those areas. We're not specifically looking at PM1 or PM 0.1. I think we're still focused on the PM 2.5 so far. In the PM1 or PM 0.1, we more look at the particle numbers rather than particle mass. So we are making a lot of observations about the particle size distribution and lumbar size distribution, and try to understand where they come from. I think the first step is where they come from. Then you can start to find out how to control that. We're also trying to look at what's likely going to happen to the ultrafine particles. It's basically PM 0.1, and how they might change in the future conditions, maybe under future net zero conditions, what the particle number is going to change. Is it going to be smaller, or is it going to potentially, it can increase as well, because a lot of things is non-linear. With regards to the microplastics from traffic, and that is a really difficult one, because it's really hard to quantify exactly how much that is from PM 2.5. We can estimate based on emission inventories and to simulations, but the real measurement is quite challenging. We also don't really know very well about size distribution as well. And if we do know very well of that size distribution, we may be able to using models to try to disentangle the actual contributions of those sources to particle numbers. It's a research in progress, let's see that way.
Excellent, thank you. I've got one more, I think that's the questions, the sort of more technical questions. I've got one more question actually, a slightly less technical one. is it's quite complex science, and some of the results are not immediately obvious, that perhaps counterintuitive. How easy or difficult is it to communicate this science to those involved, authorities and those involved in plans? Is it have you had experience of trying to communicate your findings to those actually making the plans?
Yeah, we actually have made our brief, and we explained that to Birmingham City Council. We explained that to DEFRA. So some people there, so we explain that, and they do understand this very well. They immediately say, "Oh, actually, it makes sense." So they do understand it, but making changes to the process of evaluating is going to take time. And obviously, we're basically telling them the impact is not as big as you think they are. Obviously, they don't like it. That's for sure. You know, but sooner or later they have to realize this is a real. This is, you know, you have to do it this way. I think DEFRA is quite receptive, and then they're supporting us to make this methodology more useful by local authorities.
Fantastic. Well, good luck with that. So lots of positive comments in the chat bar as well. Everyone's very appreciative, and a lot to think about, and the graphs helping understand it. So very thanks again. So a big thank you once again from us all for taking the time to talk to us. Really enjoyed that.
Thank you very much for giving me an opportunity to talk about our research.
Fantastic. And so that just leaves me to thank the Meteorological Society organisers as well to get this up and running, and IT. I think it's probably perhaps user error that I was slightly late, but we made it in the end, so that's great. Our next talk is on the 20th of January, a slight change in programme. This is being worked on, but we do hope to see you all on the 20th of January next year. And otherwise, from us all, I wish you Happy Christmas and New Year if we don't see you. And thanks very much.
Thank you.